Hello everyone. Today the lecture will be presented by Bjorn Jensen, co-header of AI Robotics Research Lab at Lucerne University. And I invite Professor Bjorn to the stage. Thank you very much.
Bom dia, bom dia. Unfortunately, this is the extent of my Portuguese for the moment. I traveled in the last couple of days through Brazil, but I am very happy. I managed, thanks to the openness of everybody, to communicate despite these language challenges. And I'm very happy to be here today and to be able to talk about my favorite subject, AI robotics. And I'm amazed that so many of you managed to come here despite the ongoing strike, despite the fact that it's a holiday for most of you. So thank you very much for joining me here in the event. Sematron, very happy. So as you have seen, I'm a professor, I'm a researcher in the area of AI robotics, and you may have heard that I'm from Switzerland. So this is bird's view of our area, Lucerne, where my school is located, where I'm working, HSLU, Hochschule Luzern. And in the front you see the city. We have several campuses, pretty much like you have several campuses here in São Carlos. We have on the right hand, on the lower right hand, we have the economics department. On the upper right hand, we have technique and architecture. And my campus would be a little bit to the left, outside of the picture. I don't have that beautiful view, but nevertheless, it's quite nice. Lake of Lucerne and the Swiss Alps in the back. So maybe you have been to Lucerne. I already met somebody who visited Lucerne. So on the left-hand side we have the Rigi, on the right-hand side we have the local mountain, Mount Pilatus, and this is where we do our research and we work on our robots. I think somehow I wanted to emphasize where we're located, and it was quite difficult to get a view on the world, where you have on the one hand São Carlos and on the other hand Lucerne. So I think if we drill a tunnel, and in Switzerland we drill a lot of tunnels, then chances are we would just end up in São Carlos or opposite from São Carlos to reach Lucerne. But that just goes to show that if we interpret this as a mathematical implementation of a sphere and we fold it somehow in a hyperspace, then I'm sure we would end up being neighbors in the dimension of AI and robotics, which is something we all enjoy doing. So there's a similarity, there's a neighborhood, and we should definitely search possibilities to exchange ideas. I'm going to start with the robotics part in a second, but just indulge me for that statistics on the home institution. So we have been founded 25 years ago, the Universities of Applied Sciences in Switzerland. That was a new development. We have currently 6 different schools, and roughly 2,000 people are working. We have 40 bachelor degrees. Who of you is studying in a bachelor degree? All of you, okay. So which bachelor degrees are you in? Mechanical engineering, electrical engineering, mechatronics. Haha, very good choice, excellent choice. I tell you why in a second. Okay, so yeah, and we have different areas where we are active. Of course, we do education, so the study programs, and we have that in the bachelor and the master. We have continuing education, so we keep contact with the people in the industry. We have applied research, and we also offer, of course, services to the community. In the last year, we launched nearly 380 new projects, most of them research projects, applied always in collaboration, or most of them in collaboration with the local industry in central Switzerland. And with that, I would like to delve into a study program. Just switch. So you all in mechatronics engineering, this is the field I work in, and we created a new study program. I have the online translation. Unfortunately, the people will be speaking in German, but we have an online translation. Oh, very bad.
Wir sind überflutet von vielen Informationen. Digitalisierung ist unsere Welt.
Die digitale Revolution ist voll im Gange mit rasanter Geschwindigkeit. Wir haben neue Möglichkeiten, die unsere Fantasie heute überfordern werden.
Zum Beispiel Natural Language Processing, Artificial Intelligence, Machine Learning, Deep Learning, Neural Networks.
Es ist ein Magnifier von unseren Fähigkeiten. Das ist das, was mich begeistert, was ich sehe in der neuen Welt.
Wir brauchen Ingenieure, die mit diesen Datenmengen umgehen können, die einfach die Zeichen der Zeit erkennen und die richtigen Technologien dann tatsächlich entwickeln können für die Zukunft.
Wir wollen die Schritte nach vorne machen, ja? Nicht die einfach das machen, was bekannt ist.
Wir müssen uns diesen Fragen stellen und die Produkte von morgen entwickeln können, die mit Informationen umgehen können, die auf ihre Umgebung reagieren können, die intelligent sind. Und das machen wir mit Digital Engineering.
Digital Engineering ist sicher keine künstliche Konstrukt. Es ist Fortsetzung von das, was Leonardo da Vinci gemacht hat. Eine solide Ingenieurwissenschaft, die Jahrtausende alt ist, mit den Möglichkeiten, die die heutige Entwicklung uns gibt. Es ist die Evolution von Ingenieurwissenschaft auf die heutige Welt.
Ich kann Sachen machen, die gar nicht denkbar waren. Mit einem digitalen Zwilling kann ich mir X-Ray Vision ermöglichen. Aber wir wollen ein digitales Abbild von unserer Welt. Es beinhaltet auch virtuelle Realität, es beinhaltet Augmented Reality. Und was alles dahinter steckt, ist Machine Learning.
Ich habe die Chance, hier wirklich die Sachen zu verbinden. Das ist die Elektronik, das ist Algorithmik, das ist Mechanik. Das sind unglaublich viele Dimensionen, die hier eben zusammenkommen.
Und diese gute Vernetzung und die Kenntnis von allen Bereichen qualifiziert sie, die Unternehmen für die Digitalisierung fit zu machen.
In dem Sinne ist der Digital Ingenieur der die Zukunft prägen wird.
Wir reden von echten Ingenieuren, die echte Technologie entwickeln, von Menschen, die tatsächlich diese Technologien bis in ihre Grundlagen verstehen lernen, was ihr Potenzial ist, das volle Potenzial dieser Technologien ist. Und das ist tatsächlich unser Digital Engineering.
Digital Engineering ist ein Investment für die Future. Die Technik ist nie erschöpft. Man kann Jobs angehen, die jetzt vielleicht noch nicht definiert sind, die vielleicht erst in 3 Jahren, in 5 Jahren, in 10 Jahren. Und das ist eigentlich, was das Leben so interessant macht. Und das ist für mich Freude.
O que pessoas extremamente produtivas, como Jeff Bezos, Elon Musk e Bill Gates, usam para conseguir fazer tanta coisa ao mesmo tempo e mesmo assim terem tempo de...
So much for my digital skills as a digital engineer. So you have noticed we try to link both worlds. Digital engineering is a new development where we try to combine elements of artificial intelligence, machine learning, digital twins with the regular engineering degree because we realized we have dedicated disciplines. We don't offer a mechatronics in a bachelor level. We offer it as a master level, but we have electrical engineering, we have mechanical engineering, we have computer science, but all these merge together pretty much like mechatronics merged these together in a hardware area, now with digital aspects, and that's something we wanted to further, and hence we created that new program. We also have a number of interesting master programs, and the most interesting for you will be mechatronic and automation, which is funnily the program I'm responsible for. So maybe there are some touch points for us in the future once you finish your bachelor degree and decide maybe on an ongoing study program. We have different areas we serve the community, so we also have music, we have social work, we have lots of other master programs, but that's maybe not as interesting. We are the youngest school of HSLU, so created roughly 6 years ago. Computer science was spun out as a separate entity, and we started on a new campus. Well, if I say we, at that time I was still in a different school, and in the last 6 years the campus was built from scratch. We have a beautiful high-rise 60-meter built of timber wood, so it's a very innovative and sustainable construction, and we are located right next to the railway, approximately 30 minutes to Zurich or from Zurich, and that is very nice for all the students, so they can easily come to the campus and use public transport. It's a beautiful campus, by the way. They're very recent, very nice, and we attracted, I think, over 1,000 students in the last 5 years, so that is a tremendous success. All working in that area in computer science, and a good part in the area of artificial intelligence. And now we also offer in the bachelor area robotics and artificial intelligence as a major. So we will lead them to the mechatronics program, to data science programs. Yeah, that's some companies we work together with, Siemens, Schindler. You probably know they have their headquarters. And then, Fraunhofer, Max und Motor, you're probably familiar with. So we have a number of interesting companies to work with. We are working in 2 major areas in our research. One is focusing on the spatial development and the society, so that despite the changes, society functions. And the other one is digital transformation of the working world. And now, how does that look, the digital transformation of the working world? I'll give you an example. This is one of my robots.
Meine Damen und Herren, verehrte Technikbegeisterte und Zukunftsforscher, willkommen zu dieser elektrisierenden Reise in das Reich der Thinking Technologies, The Impact. Heute werden wir in eine Welt eintauchen, in der Maschinen denken und Menschen nun
So here, this is the regular convention of the companies, of the economy in the canton of Zug. And the robot was given the keynote speech. And we were very nervous before that because, well, it was every live performance. If you have to get a robot to work, the hardest thing is getting it to start. Once it runs, then we're fairly on safe ground, and there we didn't have the possibility to restart. He was the first keynote speaker after the local honoratio, they were giving the introduction, so we had a politician giving a talk, and he was talking for 30 minutes without end, a little bit like I'm today. And then everybody was relieved when we switched, and that was a perfect staging ground for our robot, because the robot only was speaking for 10 minutes. It was generated by ChatGPT. We had the presentation, and we created the text by ChatGPT and had the robot doing gestures to give it a physical embodiment, an anchor of the communication, and it worked quite well. Everybody was laughing at the somehow very diplomatic jokes that the robot made, and that was quite interesting. In the next step, we had a panel discussion, so a little bit like what we are going to have afterwards, but by the way, whenever you have questions while I'm presenting, please feel free to ask. That was here staged a little bit later, so we had a panel with different people. I'm going to show you. So this is the CTO of IBM in Switzerland, and the lady is head of a personal placement agency, and then we have here the CEO of a research body in Switzerland, CSEM, and on the right-hand side the lady was the other keynote speaker. You see Pepper, and people could ask any kind of questions. was open, yeah, and then the moderator would just, the guy on the right-hand side, would just repeat the question so we could capture the audio, have it online converted to text, and feed it into the AI ChatGPT to get a nice answer. And this is the nice answer that Pepper gives. And what it was really great to see is the way these replies were created. You see it here, the people, they are reacting to Pepper. It's really, he's part of the discussion. It's not an Alexa loudspeaker sitting somewhere, but the fact that there's a embodiment, there's a real person, there are gestures that are aligned with the presentation is very convincing. And of course, it helped very much that the answers created by ChatGPT, they are very general, diplomatic, well formulated. So that was great. So Pepper was giving the first answer, and then you had the four panelists, and they were basically saying, yeah, just like he said, and I agree. So I think that went quite smooth. In the end, he was nominated. The moderator suggested he would run for the office of the politician in the next run. So I think this is more than we can ask for. Yeah, in general, what we do is we are involved in research projects in my research group. That is innovation, closely collaborating with companies. Companies come to us with a challenge or a new idea we would like to. For example, here, that might be a fitting example. Here we had a company that wanted to create lawnmowers for soccer fields. And the reason being manifold. Soccer fields, the grass is very heavily used, so it doesn't have much time to grow. If you have your greenkeeper, usually he would be sitting on a lawnmower, but that adds just another 100 kilos to the pressure on the soil, just making it even harder for grass to grow. And it needs to be mown several times to have that perfect shape. And ideally, the path you take is optimized, because on television you want the individual leaves to be folded in just the right direction to give the logo of your club or a nice pattern in the television cameras. And all this requires a lot of work. So the idea was, isn't it possible to do that with one of the robots? And this is a project that started very early on, and we could come up with creative ideas. And one of the first things we realized in this kind of project, we cannot use GPS. Because most of the soccer fields, they have these surrounding places for the people watching the game. So there are walls, there is impediment to GPS reception, it's very limited, which gives you a very coarse information and even spurious readings. And that would be terrible, because we need here a precision of approximately 1 to 2 centimeters on the robot to be able to trace the line directly to the penalty point or directly along the penalty area or the middle line. And if the robot would be going like this, it looks like a drunk greenkeeper would have been doing the job. So precision was paramount. And the first thing that has been developed in the electrical department was a localization concept for these kind of GPS-denied environments. And therefore we used ultra-wideband. So we had ultra-wideband receivers and senders mounted in the soccer area, and the robot was sending signals and measuring the runtime, and that gave us a very precise information of the robot position. And then based on that, once the robot knows where it is, you can generate beautiful patterns for the robot, how to mow the lawn and to move around, and from the displacement also to infer the orientation. This was a very nice project, except for the end. We started with the very ideas. We had an open field. We could come up with lots of ideas. Then the next thing that happens is we created a functional prototype or function concept, a prototype, and even colleagues developed a small series. and provided that to the company. The company all the while could start with interacting with the clients, and see how that worked. It worked to some extent. Unfortunately, the company finally folded, and that's the challenge of the startup parts, that even if something looks great on paper, then finally, if you're in the market, it might for some reason fail. And this is something where we are very much trying to help startup companies. We encourage our students to work in the startup area. We have a program called Smart Up, where we help them with a project in the study program so they can already work on their companies. We have lots of investing people in the area. We have a network of investors, so we try to help them get the necessary funding to get the idea off the ground, because the part for the engineering is one challenge that we have, but the second challenge that we have is later on in the market, and there we need to be very quick and work on all these challenges. So if we are in similar areas, so what we figured would be interesting is that we can easily teach the robot to tell the robot, okay, this is the area you need to work on. And I'm not quite sure why the video is not starting. So here we have one of our robots. This is in my lab. And now you can teach the robot just by walking. The robot will follow you. Here we help the robot. We are using Aruco markers, which makes it much easier to identify the person. I'm going to show you different technologies later on, how you can find people in the vicinity of the robot. And then you have two different Aruco markers. One allows the robot to follow you, so it will track the person and it will get an understanding of where the person is. And the other one is back up, because maybe you run into a one-way street and want to back up, and then you just switch the Aruco marker, and the robot will know how to back up. Another interface that we developed, because interacting with the robots, that we have a lot of information usually, and that's using virtual reality. I'll show you in a second robotic competitions in which we participated, and we realized it's vital that the people working directly with the robot, that they have as much information as possible. So what we did here is you see a 3D model of the environment. This is our campus in Horb. And you see Mount Pilatus is also in the background. It's modeled. And the student on the right-hand side is equipped with virtual reality technology. He did his master's thesis during the pandemic. So he just started, and then we needed to virtualize the entire development because we were no longer allowed to come to the university and work on the project. That was an additional challenge that we faced. And now we try to give you an idea of our campus. And now we're diving from the sky to the campus, to the green area in front of the campus. The following four buildings, they are the campus. And here you have the robot. You can give the robot a goal. It's running in simulation due to the pandemic, but it could have been one of our real robots as well. And the great thing is you can switch between basically sitting on your robot and having that first-person view, or flying in an eagle view way above the robot, and then understand the vicinity. The entire model here is based on data that's publicly available. So we have a very good mapping of the campus that we can buy from Swiss Topo, and we created the 3D representation, and then we move around. And we can also switch to the sensors. You just have seen the 360-degree camera. Here we have the 3D laser sensor. So we can overlay the old data that we previously created the map of with the actual sensor data and compare whether there are any changes and give an understanding of what is happening. Here you see there are trees which were not mapped, and that allows the operator to really dive into that situation. It's completely different to interact with the interface than just looking at the transmitted image of maybe of a limited angle camera view, where you have maybe an opening of 45 degrees. So the other thing that greatly helps is, of course, the 360-degree camera. Whenever possible, we participate in robotic competitions. So here I'm going to talk about a Eurothlon competition that was inspired by the Fukushima incident. So probably you still have memories of this when we had the issue with the NPP in Fukushima in Japan, and then soldiers were sent out to measure radiation. And it was really striking that in a country where so many robots are deployed, where there's a lot of robotic research, that in the case of an incident with really dangerous materials, still we would send people to the rescue. We would send people to take the measurements. And this is in a framework of the EU that a colleague from England created that competition and said, okay, let's check if that were to happen in Europe, where would we be? Yeah, if Japan isn't in the position to use robots, where would our robots be, and what would we need to be in that position? So they created a grand challenge that was a 1 week competition, and we were required to search for missing workers. So the idea is there's an accident and there might be some people hurt, maybe not able to move. Can we send in robots just to map the position where these people are, that when we send in search crews later on, we would exactly know where they are. We do a reconnaissance of the building, so ideally we would create a map of the building and tell the search crew exactly, okay, here is somebody and here's somebody else. And the last and most challenging part was the pipe inspection. So we would need to identify the leaking pipe that was letting all that radiation material into the environment and close the appropriate valve in the environment. This is the location, so it was a disaster simulation. Funnily, it took place on the beach in Italy. So you can imagine you have blue sky, you have sun, and you're on the beach. It's not very catastrophic, but it's just a simulation. It's a first start. And we had a multi-robot competition here. That was a major challenge. So it's not only the PackBot, our land robot that we needed to bring to the competition, but also we needed a drone. And we needed a submarine. And I have never worked with submarine robots. The drone, we just bought one and we tried to make it work. It was a disaster, but it was necessary for us to qualify. Okay, there were other universities that were much better, but the submarine, I don't know. Fortunately, we could partner with another University of Applied Sciences from the northern part of Germany, from Kiel, that have been participating in submarine challenges for a long, long time. And that might be interesting for you. Submarine robots is a great thing. A challenge is just if there's a problem, usually you kind of lose your submarine, because if there's a leakage, then everything is broken and you need to start from scratch. If that happens to my land robot, it will just run into a wall and I recover it. It's much easier. So it's a very challenging situation, and we just met on site. So we were grouped together online, and then we met on site, and we had 1 week to make it work. And that required also that the robots talk to each other. That different machines, different research groups talk to each other. And then the area for the competition was as follows. It's maybe hard to see. So we had, of course, here the harbor area. And in the harbor area, the submarine was diving and looking at underground pipelines. So it was really searching the leak underground. And once it identified the leak, it would send up an antenna, because otherwise the communication is just about ultrasound, so it's not very high bandwidth. So it would surface and then send an information to our Wi-Fi network. And the Wi-Fi network would connect to, you see here on the pier, the starting point of the robot. And the robot needed to travel 130 meters to that building structure and discover inside the building structure where the workers are and what happened to them. And we had some spectators in the area that was limiting the flyability of the drones. And we had an area around that blue button that we could discover where the piping would be, where OPIs, objects of potential interest, would be located, and we had to map all this. So here you have an outline of the system. On the upper left-hand corner, you have that control room. You have these panels that indicate which valve you have, so the robot would look at them, and then we would decide, okay, we need to close this valve. You have a mapping of the valves that the sea robot, the submarine, would identify, and the mapping of the valves. So that was an additional level of complication. So even if you tell, for example, I have a leakage on pipe 3, then you need to figure that out where that valve is located. Here on the right-hand side, you see the beautiful submarine robot from University of Applied Sciences in Kiel. The one, and the swimming pools in the back, they were used for the testing. And here we have our robot, and what you probably guessed from the dimensions, it's several hundred meters that we needed to cover the communication, under the idea that it's a disaster, so we couldn't rely on mobile phone communication, GSM communication. So that was the major development for us, that we said, okay, our robot is going to build an ad hoc Wi-Fi network that will cover all that distance. And here you see our robot in action. So it has lots of antennas. These are not fishing rods. We're not out for hunting for animals. But these are all nodes, repeater nodes, that the robot, just like in that fairy tale where the children go into the forest and they have their breadcrumbs and spread it, that's what the robot is doing. Every 20 meters it would put an antenna. And we needed to have different kinds of antenna. The one with the long rod, these are the outdoor antennas, because we realized you need to have a certain height to have a good transmission. On the floor it doesn't work very well. So we have these antennas, and the robot with his arm is automatically grabbing an antenna and then releasing the antenna, and we developed that automatic tri-folding mechanism. So the robot would just put that on the ground. This is next to the building. So now you see it's unfolding, it's dropping down, and it's now standing on the beach. Even so, we had lots of wind, so the antennas were moving around, and the robot would be folding back. The other thing you also see is the indoor nodes. So these are the outdoor nodes for the beach, and all these here, they are hacking devices, pineapple hacking devices, which we just modified, and we could drop on the floor, and they would create our mesh network. This is what you see over here. This is the mesh node dropping on the floor. We were quite successful in that competition. We went there with 2 bachelor students, so small team, and we didn't have any expectation. And then after the first run, and I'm going to show you parts of that first run, we realized we can really compete with the other guys. What you see here in the image is the 2 teams that came in second in the Grand Challenge. That is us in the foreground and Icarus in the background. And the funny thing is, Icarus is an EU project that received multi-million dollar funding. We had a very tiny budget. We just had a great robot, and we received the Texas Innovation Prize. So here we have all our outdoor antennas. This is a little bit mean. They wanted to help the robot and put wooden boards there. But wooden boards with sand, that is worse than an ice skating rink. So that's not the fault of the robot that it couldn't go there. We went directly over the beach. You can imagine the odometry of the robot was very bad in that context, in particular, since we had a track-driven robot. We have an old Velodyne 3D laser. We have that red thing is a 3D camera. We have GPS information, so we could teleoperate the robot and tell the robot go to the next waypoint. Yeah? So it was not completely autonomous. That was a decision we took initially. We said we're a tiny team. There's only so much we can do. Let's do that interactively. So the robot was moving there. In the yellow structure, this is part of the piping to be detected. And there you see the structure in which we had the control room. So it's a defense structure from the Second World War or even earlier. I'm not going to show you the thickness of the hands because then I will move the microphone, but it's at least this. Yeah? So no way that you could get Wi-Fi signals directly through. And then we had to go behind the building. Yeah. We were always hoping that the building with huge chimneys we would get next year, and then enter. Here you have an OPI that was detected with the camera, and we had to move over this kind of rubble. And the robot was distributing. Here you have one of the repeater nodes and then another repeater node. That was also something we needed to figure out manually. Now would be a good time to drop the nodes, and there we enter the valve room, and then there we can close the valves, and that was quite a success. In the same line, there we realized there would be a niche for us that is radiation mapping. Because this is something a little bit difficult to do. You need the radiation sources. They are not easy to come by. And it's a worthwhile topic because where would you send robots? You send robots where it's dull, dirty, and where it's dangerous. All applies here. Yeah, no, not dull. It's a beach, but it's dangerous at least. So you don't want to send people there. The following year, we had a competition in Austria. This is the nuclear power plant Zwentendorf, and that's a perfect testing ground because it's a complete nuclear power plant that never went into operation. Yeah, so it's completely pristine. There's no radiation at all. Yeah, Austrian government decided slightly before inaugurating the plant to have a public vote on this, to get the support from the people. They did, but not get the support. Yeah, they decided to abandon that plant. And now for the robots, every 2 years there's a competition, a hackathon going on, where we can use that environment, the real environment for our robots to see whether we can work with real radiation. Of course, we're not talking about radiation of a level we would have in an accident. Yeah, these are radiation sources that are brought in by the Austrian military. They are still strong. Yeah, we had tests in Switzerland where the military gave us sources. They were of much lower intensity. There we got strong sources, which is great for the mapping because you have less worry about the noise. And we have a starting pit here where the robots start, and then here you see it very similar to the other competition. We have one of the presumably hurt persons that the robot needs to detect. And to give you an idea of the environment, here we have a map of the environment. So there are different environments. The pit is in the upper area, and then you enter through that door. Then they close the door again because there are radiation sources within. You're not allowed to follow your robot. That is very important. And then the robot would move in there, around the area, maybe here to the right-hand side if it's open. all this time creating a map of the environment, logging the radiation and trying to figure out where the radiation sources are. On the right-hand side, you see a visualization of this radiation. So while the robot is moving, you can map radiation. Radiation mapping requires time. So usually you do an integration over a time interval and get a measurement. And for us, it's clear to see here at the starting point, there's a source somewhere in the area, and here we're coming close to another radiation source, so that helps already the crew to identify where are dangerous areas. This is only important in case of an accident. Regular operation of an NPP, people would know where radiation are. There are two states of an NPP. Either it's operational, and then the people have like a map, and they know exactly, don't go into this hallway because there's too high radiation, and here I can stay for a couple of minutes, it's not a problem at all. These will be verified every day, they will have regular measurements, but never anything changes. And then there's a state of revision, where you turn off basically the radiation part, and then you have lower radiation, this is the other state. But if something happens, then you have this challenge. It also applies to something that's happening nowadays in Switzerland. That's the deconstruction of the NPPs. As soon as you put them out of operation and you deconstruct, you remove the walls, you remove the shielding, then the distribution of the radiation is no longer the same, and people walking there and working there, because it's still a lot of manual work despite all these great advances in automation, then people would need to know, okay, here I can stay 10 minutes, that's okay, that's allowed. And this is where this kind of maps come in very handy. Prior to that, the search crews need to use something that's called orthogonal search. So how does that work? You look at your measurement device and you just walk up as long as it increases, and when it starts decreasing, you know, okay, I have to back up, and now it's either left or right. You toss a coin, you try right, oh, it's going down, you go to the left. You can imagine how cumbersome that is, spending all that time being exposed to radiation, just to identify the source. And it's so much easier just to send in the robot, and the robot would tell you, okay, here is the radiation source. This information is a little bit coarse, so we went further. Here we developed a 3-point measurement, so our Mercedes star measurement. So the robot would be standing somewhere, and we would take measurements. So this is 4 times accelerated due to that time integration that we need to do. And you see the radiation sources just behind the robot, the blue elements there. And then from these 3 points, we could, of course, calculate where the source is located. Fortunately, radiation sources, they decrease quadratic with the distance. So there's only the closest one that is important. And on the right-hand side, you see the radiation map we created. So this is a different environment. This is the upper floor. This is really the nuclear power plant. And we were moved there with an elevator. And the robot got out of the elevator. And the first thing it did was it performed that 3-point measurement. And then we knew where to look for the radiation source. It was on the opposite side of the area, and we could go there, and you see the robot, when it reached that area, there were pen-sized small rods all over the place, and the idea was, okay, there was an accident, a bar was broken into small pieces, and now the robot has to distinguish, there you see the robot moving in that area, the robot has to distinguish between sources which are really radiating and sources which are just metal. Because the metal or low radiation sources, the human helpers can collect, but the high radiation sources, the robot would grab and then bring into that bin with the radiation sign and drop it there. And all this is under time limit, of course, and hence it helps enormously that we have that possibility to compute, okay, this is where we need to go, because the other teams, they were running around the environment and trying to identify where is the radiation, as we did in the previous run that you have seen. Yeah, and here it's dropping everything in the bin. Yeah, challenging environment for the robot, yeah, because they're not solid walls, there are obstacles, and we need to operate in that area. Now I'm switching a little bit. Of course, it's great if robots and humans can work together. Here in the previous example, it was more sequential. The robots were preparing everything, we're creating the map, we're giving the information, we're collecting the information. But with the advent of collaborative robots, we have also the possibility to work closer together. So what we have here is a setup in the Swiss Competence Center for Robotics. It's not located at our campus, it's located on the opposite side of Switzerland. And there we try together with companies to do a gear assembly. You're mechatronics engineers, so you have a very good idea what a gear is. And here the collaborative robot tries to assemble that gear. So it takes different parts. And the great thing about gear assembly is you need your force, you need to wiggle things to fit. And this is a technology the company specializes in. And what we brought to the table is the identification of the different parts. They're very complex parts. And the idea is that they can be put close to the robot, and then the robot would identify them and work with this. We use machine learning for the task. Machine learning requires lots of data. And that makes it prohibitively expensive in many cases, because somebody needs to prepare that data, needs to label the data, and needs to work on all this. So here we used an Intel RealSense camera that gives us in-depth information of the pieces. And then from that information we can use connected component labeling, identify the objects, take the objects from different points of view, create a big database, and then just train one of the networks. I believe we took a convolutional neural network that now identifies the different shapes of the gear. And it's more than it seems. We only have 10 elements that we assemble, but every time you put one piece into another, you create a new kind of piece that you need to model and teach your robot. And this is something where people can be standing next to the robot. We also have a part where we do people detection, which I'm going to show you in a second. Very similar, using the same collaborative robot, we are working towards applications in hospitals. That's a major challenge. We realized in many countries, in Switzerland as well, there's a high turnover in the people that are employed in hospitals. It's less the doctors. The doctors have tremendous stress, but somehow they remain in the hospitals. But in lots of the assistant roles, in the nursing part, in the assistance to the doctors, they have difficult working hours. At least in Switzerland they have. Long time. If you work in surgery, you spend most of the working day in a closed room without seeing any sunlight. It's very special. You start early in the morning, you go late at night, you have to handle the loss of life because it happens. So it's a very challenging environment. And some of the tasks, they are prone to automation. So we were discussing with a hospital in Switzerland saying, hey, we have robots. Here we have a mobile industrial robot, MIA, the white station, and we have that universal robot on top. Why don't we put it in the area of the surgeon, and then the surgeon can just tell the robot, give me this kind of tool, and then we can take the tool and we can work with it. Now you have an idea of the tools of the surgeon, knives among them. So even if the robot is collaborative, it's only as collaborative as the tool. And if you hand over the tool like this and you slit the hand of the surgeon, you only exacerbate matters. So you really need to be collaborative, you really need to be aware of the environment, but you also need to be able to find your medical instruments. So here we have a set of medical instruments that we learned. So similar to the previous example, we taught, and we have a 3D model of surgeon environment, where you have your universal robot, you have the surgeon, you have the patient. So you're not allowed to cut the patient, that's the surgeon's task, and you're not at all allowed to cut the surgeon, that's nobody's task. but you just give the tools and you help the people. And fortunately, we found a database. There's Kaggle, yeah, you have heard of, and we found a database where they have an enormous amount of pictures to learn from. So we could train our neural network to identify these tools. And here you see the results. That's a confusion matrix that basically tells you how often a particular tool is taken for a different tool. Since the main diagonal has the highest values, that's good, because that means that most of the time we identify the correct tool, which makes sense, because surgeons, they don't like if they tell the assistant robot, give me the myoscalpel, and then it's the hammer, because then it takes much more time. We have some confusion. You see on the right-hand side, there are some light blue elements. These are mainly the background. You know? And the reason being that we have here a reflective surface, and also the shape of the background can be confused with some of the instruments. This is good news because subtracting the background is something very basic in image processing, so that's something we can do quite nicely. The detection here runs on YOLO, not the most recent, the number 8, it was the previous one, so we get that information quickly. So the robot can really do that while it's moving. This is great, so the robot knows where it would need to take the tools, then magically it would move it to the surgeon without hurting anybody, and later on it would just grab the tools again and put it in a different tray, because that's the used tray, so they are no longer sterile. This is the additional challenge in hospital environments. So important for that is to know where the people are. And this is what we do here. We have people tracking. So we have a setup, a 3D laser. I think it's Velodyne laser that we're using. And we have a 360-degree camera where we have a YOLO algorithm for people tracking running on top. And we can get both information, the angle, and we also get the distance to the robot. We are working on getting more information, in particular out of the point cloud, so we would like to know the posture. Yeah, but currently we just know where the people are, which gives us good information when planning the trajectory for the robot. Yeah, so the robot would not hit accidentally anybody, and we can put that information in addition with the 3D model we have here. We can put it and let the robot plan the perfect trajectory. Now, another possibility that we came up with to detect persons is Wi-Fi information. Yeah, we stumbled upon that possibility, and I convinced a student to start a project on people tracking. I wanted him to focus on cameras because I know that works. And then he said, hey Bjorn, you gave me a bunch of reference and there is that Wi-Fi solution. Can I work on this? And that put me under tremendous pressure because you need to give the students the possibility to succeed. So we had a backup plan. And here you see the student in the parent's home taking measurements. So we have a setup here of Wi-Fi routers and a camera. And the camera gives us the ground truth. So we know whether there's a person in front or not. Yeah, we can easily compute that and use that information to train a neural network. So what the student did, he was training actually two kinds of neural networks, and it relies on a particular kind of Wi-Fi router. So if you want to work on that, it's particular Wi-Fi routers which give you information to the channel state information. Now the channel state information is sampled at a high frequency, and here we have routers with 3 antennas. So basically for each antenna you get the phase shift and the damping measured in the channel state information. And this is something that's very useful because persons basically, they are huge reservoirs of water. So they highly impact radio communication. So the channel state information gives us very good information where persons are. And learning from ground truth, here we had just a video. We could easily collect a huge amount of data, and we could train the network. The student could train the network, and that allows us to tell, okay, there's a person. This is a first step in that direction. You see there's some noise, but not very much. It's clearly obvious where the people are. It's clearly obvious which posture they have. And the great thing is, this technology is not at all invasive. If I were to ask you in your home to install cameras so we would know what you'd be doing, you would say, not participating in the study. At least I hope you would do that, due to privacy concerns. But if you use that Wi-Fi setup, everybody has Wi-Fi at their home, and if we have 2 of these systems, we can, without disturbing you, without even knowing it's you, we don't see your face, we just see there's a person, we know what is happening. And I see lots of opportunities here in the area of elderly care. When people, they get older and older, they are more afraid of living at home alone. They might fall, nobody might notice. With a setup like this Wi-Fi detection, we would quite easily notice without invading the privacy in any case. So this is a new development, and now we have ongoing projects because we believe it's much more than a 2-dimensional information we can get from the Wi-Fi people tracking. This is the digital festival. It's again our Pepper. It's now interacting with the people. This is a colleague from the university, and it's doing a conversation with one of our robots. So it's a very sequential setup. There's a lot of background noise, as you see. There is our chess computer. There are legged robots in the background, and the robot listens to you whenever it holds up the microphone. So it needs some getting used to, and then it processes the answer. Once again, interfaces with ChatGPT, and then comes up with a very nice answer. There was a public demonstration 2 days in Zurich, and at one point there was a woman visiting our booth, and she was very skeptical, and then she said, can I talk to the robot? But not excited, very, very skeptical. So she sat down, and then she challenged the robot and said, do you know that art house movie from, I forgot the title, and I said, oh my God, art house. I wouldn't have known the answer. But due to the amazing complete database of ChatGPT, the robot just answered, yes, of course, I know that, and it's a very important movie, and I like this part, and I like this part. And then she spent 30 minutes talking with our robot. So I was quite happy that we managed that challenge, and also in that environment with lots of noise in the background. We want to make robotics accessible, but also very safe. You realized that when I was talking about the hospital, where we had lots of constraints. So here we have another master's thesis. You see Alex Petrovic, who developed the robot. This is a parallel kinematic robot. Well, you're a mechatronics engineer, so you know that. And it has been developed with support from Maxon in the Young Engineering program. So we received the motors and we received the controllers. And the idea was to enable people to play chess, but physically, not in a simulation, but physically with a robot. And if you Google, if you look a little bit, you find there are accidents. So there was one, not with our robot, but there was a competition, I think in Moscow somewhere, and the robot unfortunately mistook the finger of a child for one of the chess pieces. And it grabbed and held on to the finger, of course, because it was a chess piece. So we figured it would be better to have a safe solution and clearly to separate the workspace of the robot from the workspace of the human players. So we have the table, which is completely covered, and we have the parallel kinematics below with all the singularities that implies. And it would move, and you see the holes in the chessboard, so we could identify the chess pieces from below by colored rings. Well, it's not very challenging, but it's a way to do that. And then we could identify the move. And since our research group is called AI and Robotics, we thought that's a perfect application. We have chess as artificial intelligence, and we have the robot. And just to show that we can do it, we let the robot play at least 2 tournaments. I have to admit, in the beginning I wanted 4 tournaments to have that nice Swiss cross in the setup, but it didn't work out, because then we would need an additional degree of freedom for the robot. Otherwise, with the singularities, it wouldn't move. So here you see the robot, the human player is moving, and the robot is moving the other part. And on the opposite side, you have a different player. Well, in this case, it's the same. And then the robot figures out what happens. There's a camera monitoring from below, so it's all encased in the table. And then this is the direction. So we can have a game. We're still working on it. There are some things we would like to improve, in particular when we win one of the figures and we put it aside. But it's a very nice demonstration, and it's something, a master student in mechatronic and automation developed in his final project. Other projects we're involved are more in the artificial intelligence area. So here we have on the left-hand side a garbage truck, and we optimize the routes. So it's a traveling salesman problem, which is very challenging and can become very complex. So it's NP complete, but if the graph is sufficiently small, then you can come up with the optimal solution. And this is just a smart part in that to represent the graph of an environment, of a city, maybe that you get from OpenStreetMap, to make it computationally handleable, or come up with approximations where you know that within a certain percentage you are in an optimal area. On the right-hand side, you see a nice project we have with a Swiss Railway. Swiss Railway is going forward to become more sustainable. You see the area of the tracks. There is no vegetation at all. Currently, this is because the SBB is using glyphosate. So this is just some vegetation poison that they spray once a year. And they would like to get rid of that to become more sustainable. And what would be more sustainable than mechanically fighting this vegetation? So we are developing a robot together with the mechanical engineering department, where the robot can travel next to the rails, identify the vegetation, and then just cut it off or pull it out or burn it, or somehow in a sustainable... We still destroy that kind of vegetation because it's not supposed to be there, but we do that without impact on the water, for example. You see in the video, it's very shaky. That's the rubble on which we are moving. It's the environment. We run an identification so we can identify the catenary poles where the high tension wires are connected to. They are mapped, so we can use that for the localization of the robot. And we also identify the workers. We could identify more, but there's not to be supposed many more objects. That's what we do. On the right-hand side, we did a classification. We have 7,500 kilometers of railway. For Switzerland, that is huge. I realized in the last couple of days that Brazil is a little bit larger, so you might have even more tracks to cover. And here we did a classification. You see different colors because there are different concepts. You could have a lawn mowing robot like you have in your front garden, or you could have a robot that is traveling day and night in one direction with recharging stations, and the different colors indicate that. That's part of the artificial intelligence part brought to that project. This is something for you. We participated in the RoboCup in 23. Well, actually, we are participating this year again. And what I have heard is that next year, the World Cup will take place in Brazil. Please verify. To me, it came as a rumor. You're probably familiar with the RoboCup. It has different leagues. You have the soccer leagues. You have omnidirectional robots playing soccer. You have the Now robot playing soccer. But if it comes to your country next year, I would be very happy to see you participating with different teams and competing. We are competing in a very special league that's called the Logistics League. The Logistics League, why did we select this? Because, well, we have that artificial intelligence and the robotics part, and I'm not sure how that is in Brazil. Maybe you can teach me, but in Switzerland it's extremely difficult to convince companies, let me take over your shop floor for the weekend, I'm going to optimize some stuff. Trust me, I'm an engineer. Yeah? It never worked. So here in the competition, we have a challenging setting. So you see all these Festo workplaces distributed in the 3D rendering. They are put in different places every time, for every competition. So the robot needs to understand its environment, and then it needs to produce C0, C1, C2, and C3. This is a little bit difficult, so let's make it more palpable. You see these objects in the upper right-hand side. It's basically a burger place. Yeah? So you tell the robot, I want the plain vanilla burger, and then it just gets the buns and the meat and puts it together. That's the black and gray stuff. Huh? And maybe you want your burger with bacon, or maybe you want it with bacon and cheese, and then you have these other stations. And that means the robot has to figure out a path. Yeah, in that area, you have 3 robots, so you can distribute the productions of the burger if you want. Yeah, and you have on the other side, you have the competing team also with 3 robots. So it's not a static environment. It's not a completely known environment. It's even an adversarial environment, if you want, even so everybody's playing fair. It's a very nice league. So you see the robots moving to the different stations. You have Aruco markers to identify.
We are now in the production phase. In the production phase, we get orders from electronic referee.
Huh. So, and you see how that moves. It's not the same scenario, just to give you an idea. Here on the left-hand side you have Robotino robots from Festo, a little bit pimped, so they come to the height. You see that in the 3D rendering. And on the left-hand side you see a ROS environment which we use for all our projects. I haven't shown that in the details previously. You have a map here, it's a map generated by the robot, your coast map that allows you how to drive. And then the intelligence part, you have that referee station that tells you, I need a C3 in 3 minutes. And then the artificial intelligence needs to figure out, can I deploy my robot to produce that in these 3 minutes? If yes, I accept the offer. And if not, then I pass and move on to the next. So yeah, that's one of the leagues, besides soccer, besides social robots, and I hope to see you in that competition next year. We have a bunch of LECT robots, and I heard there is or will be a bunch of LECT robots, at least here in Sao Carlos. We helped them to discover HSLU. So this is the campus we built 5 years ago. This is a lecture building. Robot enters. We have a Leica 3D laser on top of the robot. It enters into the lift. It's a little bit marketing. The robot does not know how to operate the lift. It's not that technically it wouldn't be doable. I asked for the API, but the service responsible for the building told me he wouldn't give it to me. So, and this is the robot doing kind of an exploration, and you see the building that we create. This is BIM of the entire lecture hall that the robot can build. And this is a great application. We developed that together with a company, and here we do tunnel exploration. My co-workers were allowed to name the robot. We have 2 of them. They came up with Bonnie and Clyde, hence the name. And then we have lots of sewage tunnels in Switzerland, and by law they need to be inspected every couple of years. I think it's every 2 years. An inspection of sewage tunnels is, it sounds easier than it is, because here you see us preparing the robot. If you do that manually, you have to open the tunnel a day before to let air come in. Sewage might be poisonous, So you have to take precautions for human inspection. If you send the robot in, there's no risk at all. At the worst, you lose the robot. The same technology, together with Tologa, the company that is interested in that. This is the 3D model we created from the tunnel. The tunnel is 1.4 kilometers. So we put the robot on one end and we send it, and it moved using basic wall following strategy. So it's very simple, very robust. And then it was just collecting the information and combining it to create that 3D model. I have to admit, with the Go 1 robot we had to switch batteries in the middle of the area, so it's not yet a product, but I think we can agree that we can increase the battery size, and the robot and now can move through this environment. Every now and then we also have fun with our robots, so we had snow a couple of weeks back. This is before Christmas. This is our new Spot robot, and we were preparing for that snowball challenge. With our projects, we hope to be able to make robotics jump. Here we have a new gate that was developed using reinforcement learning, and that worked with that. If you are interested to get in touch, there are many possibilities. Talk to your professors. We are a very international campus. I'm involved in a study program where the head of the program is a native English speaker, so we have lots of courses in English. We have lots of courses in artificial intelligence and first of all robotics. You can also come for an intensive week over the summer if you want, and that is a possibility to get international experience. We are very interested in developing double degrees also in the master area. So I'm responsible for mechatronic and automation, and I would be very happy if we could have a regular exchange and see how that leads to new projects. Well, I've shown you many examples of robots. I'm in the fortunate position that I'm not the only one working on these robots. So there are many people in the team. This is outdated. We even have a new colleague now. I think the robots, they are fairly accurate. We don't have a new robot yet, but we're working on this. And that is my insight into AI robotics. Thank you very much for joining me. And I'm looking forward to your questions. Thank you.
Thank you, Professor, for the amazing lecture. And now we are going to be opening for a few questions. By the way, if you don't feel safe or is kind of in pressure, you can say for us a question in Portuguese and we will be able to translate it. Okay.
First of all, great presentation. I really liked it. My name is Fabrício, and just out of curiosity, do you have a perspective of when these AI robots will have a domestic use like companions or assistants?
You see, thank you very much for the question. It's an easy one to start, hence I'm hesitating. I think we are already going in that direction. We have some elements of companionship. We already have robots that are used in particular elderly care for conversation. There are these, I lost it. So these nice sea animals which are very nice to touch, so people could caress them and talk to them. Probably you're aiming more for general purpose applications, and there I think we still are challenged by the complexity of the environment. Now there are first steps being done right now. If you look at my kind of robots, we still do the mapping kind of old-fashioned. So we move the robot around and we generate a 2D map. New approaches, which are current projects for my students, is that we leverage large language models and databases, 3D databases of the objects. So instead of moving around here and trying to understand each chair, I would leverage that information, and then based on the kind of robot I could navigate in this environment. This is probably one of the prerequisites, that I have a good understanding of complex environments and that I can share that information among different robots. And then if you take the robot to your house, it would recognize a chair, it would recognize the table. So you were asking about a timeline, or a little bit in direction of the timeline. I think it's safe to say 10 years. Yeah, because this is close to my retirement, and if it hasn't been done, then it's up to you.
Thanks.
Thanks for the question. More questions? Yes? I think you get a micro.
Do you see any type of pattern on solving the problems, like getting the real data of a sensor and traversing it to abstract information from the processing of an AI and get those abstract results and passing it back to some real stuff like the movements of a robot?
That is a major challenge. Yeah, it's as simple as that. If we look at the two examples where we were assembling the gears, for example, no database available, so it's up to us. Of course, we have the robot, so we can automate this. It's a very limited setting, so it's feasible to collect hundreds of images, which is what we're talking about, and do the processing. In the medical instruments part, this is something where more research is going on, and there you can share it. So the very creation of that shareable databases, that's a research topic in itself. And the more we have in that area, the more you can do. Maybe you want to have a look at there's work in Google research where they combine different database sources as well with the readings they have currently from their sensors. And that can jumpstart any project in that area because you can leverage that new database.
Thank you.
Thank you. More questions? Yes.
First of all, thank you for the presentation. And my question is about the grasp and pick problem. For example, if I would like to pick a complex geometry object, so for example, how can I choose the kind of grasp and where I will pick this object?
Okay. I think there are two, broadly speaking, there are two approaches. One is if you have CAD models of the object, then there are tools that optimize the grasping points. And you can try to learn that in theory and then apply it and just pick it and everything works smoothly, supposedly. Here in our project, that is the knowledge of the company, ICA, we were working with, and they use reinforcement learning. So they try and try and try, and also the forces they apply, they try, and then they can grasp the object, but even more challenging, they can insert the object, because this is something we do very well. Yeah, if something like you want to put in the power cord into the plug, and then it's just not entering smoothly, and we have an idea how much force we can apply. Yeah, and there's a certain limit, and then we will break everything. And this is something they learn with reinforcement learning. This is the other possibility if you don't have access to the 3D models of the object.
Okay, thank you.
Thanks for the question.
Thank you for the lecture, Professor. I have a question regarding safety. We are having parallel to the presentations, workshops, and one of them is about cryptography. Mm-hmm. And yesterday we learned that how easy drones are hackable. Mm-hmm. And do you have any concerns about safety, or do you protect your systems against such attacks?
That's a huge can of worms. And a very valid question, by the way. So you have seen we have these universal robots. You can just, maybe you did already, you can Google how many safety critical issues there are reported, and then you start thinking about applying these robots in safety critical environments. I think currently it's something that's strictly separated. We focus on mechanical problems. We have some electrical components. We start using artificial intelligence, but also in our school, we have a complete research group on cybersecurity. They never have heard of robots. So there is definitely a step in addition to be made. Maybe we will do that because the new head of the program, he comes from Korea, and he also taught robotics, so he might be aware of that. I'm very curious how that works out. A little bit more from the technical side, I would argue that if we cut the communication interfaces, we would be much more safe. So if we make our robots more autonomous, then maybe we can get rid of lots of these, unfortunately, existing communication problems.
Makes sense. Thank you, Professor.
I think there was another question over there.
First of all, good morning, and thank you for the lecture. It was very inspiring and interesting. My question is about the environment and the things that we see today. How do you think the AI and robotics can help to save, I guess is the word I can speak, save the environment, like registering, sorry, my bad English, the emission of CO in the air and these things, and how we can do some stuff to save our planet for the future generations.
Okay. 9:30, we save the world. Very good. Thank you very much for the question. I think robots can do quite a lot. So also in the projects we looked at, if we get into areas where it's dangerous, we have a lot of advantage by automating the process. Maybe to give you additional examples, I talked to a Korean company that created robots, boats, that are applied after oil spillages. So this is something that helps. You can just have a fleet of these robots and they would avoid even bigger disaster. The cost of the boats doesn't matter in that case. We also talked about the possibility of using that to fight algae, because with the climate change that's becoming more and more unavoidable, we have heating of the water and we have more algae, and then we have a major impact. So the same boats, they could on a regular basis, they could collect that information. So there is a possibility of fighting the symptoms, where I see application of the robotics part. Probably we're better off fighting also the sources. But this is a burden onto us. I don't see well, maybe the robot could slap us on the wrist whenever we are not energy aware, but this is as far as it gets. So it remains something where we need to work as well. I hope I answered at least part of the question. Thank you very much.
Hi, my name is Anna, and I'm from the Federal University of Uberlândia, which is not near here. First off, I wanted to say that we have a soccer league robotics team that will be participating in the international competition next year, so we will most definitely be saying hi to you if we find you there. But my question is more in the social realm of robotics. I have always seen studies on ASL, American Sign Language, and like students that develop robots that can like track people signing and reproduce kind of, but I've never seen them in action, like in actual public spaces and being like just let out there and interacting with a lot of people on a daily basis. So I wanted to know your opinion on whether or not that will be viable in like the next couple of years. Like how fast would that go? Because of, the robot that got the kids' fingertips and like thought it was a chess piece. So I don't know if that would be like, you know, like a good communication system from right now. I wanted to know your opinion on that.
Thank you very much. Yeah, I think sign language is a very important part, because when we talk, we gesture, and it's even more important if we want to be inclusive. The pepper is a design achievement, so it looks very accessible. It inspires a lot of ideas. I wanted to play table foot with the pepper because of these nice hands, and unfortunately I learned there's only a single degree of freedom, so you only can do this with the hand, and it only can lift up to 10 grams. So it's important to look human, so we have the 10 digits, but we don't do anything with it. Now we both agree replacing the hand is easy. You know? So it's not a question of having the 10 fingers, and the sign language alphabets, they are already available, they are automated. A couple of months ago I talked to somebody who had a project with the Swiss television, because they wanted an automated way, like we have the automated translation of the initial YouTube video, where you can have that animated person in the lower right-hand corner doing the gestures. As soon as we have that, we can interface that quite easily with the robot, but we just have to cut off Pepper's hand. Yeah. And by the way, I'm looking forward to seeing you at RoboCup. Thank you very much.
Okay, we'll be seeing each other, surely.
Excellent.
I have a question regarding the radioactive environment competition. Do you have interference in your readings of the sensors?
Not that we noticed. We were worried prior to the competition, because this is in Fukushima. This has been a major factor. Yeah, in order to they sent in robots into the NPP, as you probably know, and the way they set it up is they brought a Wi-Fi router, cable bound, up to the main entrance, and then on the other side as well. So the robot was cable bound, and the Wi-Fi transmission was only through that door. In our settings, we could rely on Wi-Fi communication. So this is something we don't touch. We did touch in the beach example, but it's very difficult to focus the areas. We have a small team, so we said, okay, let's create the radiation map and bring that back to the persons. We don't have any shielding on the robot either. You know, that's something we could be done. Yeah, but just without the real application is not something we do. We did not have any impact, even if we were close to the sources, on the camera, on the laser readings, so everything was working fine, even so the sources were a little bit stronger than usually. Yeah.
Thank you.
Thanks.
That works. Thank you, Professor, for the lesson. That was very good. I have a question about a provision for your own study. You work in the robotic fields about radiation, about disasters, and how much time do you think that we need to the protocol of rescue of doing? To deal with disasters, not only by radiation, but earthquakes and tsunamis and all the stuff. The protocol will be used robots. When you think that will be a reality in Europe and the other parts of the world, probably in the UK, United States, Japan, in Brazil will take a little more time, but when you think that will going to be happen?
When you speak about the protocol, are we talking about that the rescuing would be done completely by robots, or that the first robots will be deployed for rescuing?
When to be normal to this happen.
Okay. So yeah, it's an active area of research. You mentioned that you are working in that area. I'm not sure whether you use existing robots or whether you build the robot from scratch, because this is an area where also the type of kinematics is very interesting. There are robots track-driven like mine. There are lots of drones. There are snake robots, all kinds of robots. So you can be very creative in that area. The challenge is manifold. It's an engineering challenge. We have first drones that are part of regular disaster teams. They come and they fly with that drone because it's something you can buy off the shelf and you can integrate easily, and it gives you a first impression of how things have changed. If we talk about robots on the ground, there, I think we still are working on it. We have a regular competition in Switzerland where we have legged robots using reinforcement learned strategies of motion, so they're not simple gates. I think they are very robust. They are getting robust, so you could move over that area. Challenge is, you were asking when the teams are using that, it's the funding of the teams. Yeah, because all these emergency scenarios, they are highly attractive because our robots are saving lives. But on the other hand, if we talk about the legged robots, it's several hundred thousands of dollars of investment, and usually it's just money that is not available for the teams. So they can buy a drone because that costs $1,000, yeah, but they cannot buy the legged robot, and that limits it currently to the close collaboration of research teams with particular teams that do the search and rescue, and this will take some time. Finally, yeah, it just boils down to having an accident and everybody realizing, oh, well, we could have bought these robots and then we will have the funding available, unfortunately.
Thank you, Professor.
Good morning, Professor. Thank you for your talk. I would like to ask a question regarding the use of the development of products that use AI and robotics. More specifically, how to go about developing a product and manage a complex product. So, for example, you're developing a new product that uses these two technologies. There's a lot of work to be done, like with the, gathering the data, being able to label it, and developing of a model to be able to use it inside the robotics. Inside of part of the robotics, you need to develop the electronics and integrate all of these things. So I would like to ask for your tips that you would be able to offer in how to go about the development of such a complex product, and how to focus to make sure you're able to develop something that is successful in solving the desired problem.
Thank you very much for the question. I think the main part is in your question. You are aware of all these challenges, and once you are aware, that's the best part of being prepared. I never had a project where I encountered all these kinds of problems. So if we look at the ones we were talking about, we had sometimes the problem of gathering data and labeling the data. This is something we try to automate. There are probably also possibilities of sourcing it out, but we are reluctant to do that for the moment. So we didn't have to do that. We try to use the robots to do that task for us. Then I think your question also touches the multidisciplinary area of mechatronics and automation. Our focus is on the part where robots and AI merge, so it's a very small field. And if we need to develop, for example, an entire robot, we would partner. Yeah, we would outsource because this is not our competence. Yeah? In the example of that SBB, the railway project, we have mechanical engineers, they are building the robot. So we don't need to do that. Of course, we talk to each other, yeah, because there are touch points, but this is something we do. In general, where we are located in the product development is in that early phase. Yeah? So you might remember that slide on the lawnmower, where we come up with ideas because the company is not an expert in the robotics AI area. So we can gauge and we can suggest these might be technologies that could solve your problem. And I emphasize the could. And then in Switzerland, we have a funding agency InnoSwiss that helps manage that risk. So that's something we source out if you want. And then the company and us, we would sit together and say, okay, let's assume this technology solves the problem. A project to make that ready for a prototype, not the product, but a prototype, would entail these and these steps. You know, so we have somebody working on it. And it's high, there's a high risk of failure. You know, so it's not something an investor is happy to take on. Yeah, but there we can apply for funding and we can get the funding from basically the Swiss government, provided that the knowledge that we develop is given to the company. Yeah, so we have a knowledge transfer to that company which would be active in AI robotics and, for example, go to market with a lawnmower. So they would not rely on us after that has been developed. This is another part of the management that we say, okay, we go up to we have that functional types, and then we have the prototypes, and then we hand it over. Yeah? And the second task, since you were talking about the product, this is something the company does. It's not funded. Yeah? It's something investors are good at, yeah? Gauging the market, doing the marketing and all that. It's not something we do. Thank you very much.
Thank you.
Now the last question.
Good morning, Professor. Thank you for coming here and sharing with us your project.
Same to you.
I would like to ask about a different view. I would like to ask about the design of your robots. And recently we've seen robots that look like humanized or something that looks like human beings. And looking at Pepper, he looks like very sympathetic. So, and people interact with it, and people laugh. So, how do you think about the design? And do you, when you project it, do you think about something like more sympathetic, or and how do you think this affect the results of your research?
Thanks for the question. Couldn't have been better if I'd placed it, so thank you very much. This is a vital question. And you mentioned Pepper. I think this is the pinnacle in that area. It's not from a functional point of view, but from that interaction point of view. So there are a number of aspects. And I'd like to go back like 25 years nearly. We were in the position of setting up a public exposition. Yeah, I was a PhD student at that time, and we could put 10 robots into a museum and guide visitors through the museum, explain the exposition artifacts, interact with the persons, and then move them out of the exhibition. And of course, being engineers, we were concerned about how does the robot localize itself. So where am I? Yeah, where am I going to go to? So what is my next goal? How do I get there? Path planning. So we developed lots of technologies. And we had that differential-driven robot, yeah, running a real-time operating system, Oberon, developed in Switzerland at the ETH Zurich. And then we realized, okay, yeah, now we have that robot, it's moving around, but there are visitors. So somehow we need to interact with the visitors. Okay, we designed a mechanical face. And then we invited designers, industrial designers, and said, make it look good. And the industrial designers, they said, hey, you're nuts. Why are you coming now to us? In 6 months is your exhibition. You should have started the discussion months ago. Yeah? And the only reason we talked to the industrial designers was, you imagine creating a differential-driven robot, it's circular. All of the time it's circular. You know, it helps in navigation, so we did it. But if your base is circular, and as an engineer you try to make a form out of it, you build a woman because she has a skirt. Yeah, it's circular. That's just our design. And then the industrial designers, they came to the safety. You know, they cut the base. They had a pole a little bit to our height. We put a mechanical face there with eyebrows. No mouse, because synchronization, synthesized speech to mouse was not possible at the time. So we had an anchor of communication. Yeah, that's vital. And the underlying principle is be honest. So we were honest. What we created is a robot. we offered interfaces for human-robot communication, a face, facial expressions, synthesized speech in all of the 4 languages, no 3 languages in English in Switzerland, but it stopped there. We did not pretend to have artificial skin. We did not pretend to be a human, because this is scary. What we're talking about is called, well, you know that, huh? It's the uncanny valley. Robots are appealing as closer they become to our way, but then you have that Frankenstein effect. If we are too close and we still realize the small differences, then it scares us off. So if you look at recent developments, there are lots of robots that are more performant from a functional point of view than the Pepper, but they are scaring. There is in Japan, Ishigulo creating lots of robots where you have 20 degrees of freedom only for the faces. You have a latex skin. In the photos, you cannot distinguish the real guy from the robot. It's just scary. For me, it's scary. And this is the guideline. So be aware of that uncanny valley. Steer clear of it, or in a couple of years, maybe jump over it. And build a real robot, a real human. And think of how the people would like to interact with your robot. And this is what the Pepper does greatly. You have your face, you have facial expressions, you have the hand, all that's available. So if you design such a robot, that would be my advice. Maybe you have more degrees of freedom for the fingers so we can have the sign language. Thanks for the question. Thank you all very much for joining me this early in the morning. I hand over the mic to you. It was a great experience. Thank you very much.
Thank you, Professor, for your participation. It was an honor for Sematron to have you here.
Thank you very much. Thanks.
And now we are going to make a giveaway, and I will give some comments, but for better understanding, I will make them in Portuguese, okay? Vamos lá, gente. Hoje é o último dia de minicursos. Vão ter diversos, inclusive um novo minicurso que é aberto da Alura. Hoje à noite, às 7 horas, a reunião vai ser no E1 novamente, para depois que a gente distribuir vocês para os lugares corretos. A gente também pede para vocês chegarem cedo nas palestras, continuarem usando os copos do kit nos coffee breaks, é importante para a gente evitar o desperdício de plástico. E, por fim, eu digo que a próxima palestra é sobre Stock Car, uma palestra muito interessante sobre inteligência artificial na indústria do esporte, então conto com a presença de vocês. E agora vamos para o sorteio. Só um segundo.